as a continuation of wave mechanics, which will eventually continue into wave optics later. So as a continuation of wave mechanics, we look at the second part of mechanical waves, which is longitudinal mechanical waves. Which is basically physically, that is sound waves. So as we've seen earlier, by definition, what is a longitudinal wave? It is one where the medium particles displace waves such that the medium particles oscillate along an axis which is parallel to the propagation of energy. Instead of being transverse or perpendicular, it is parallel to the direction of propagation. Okay. So the physical example of one-dimensional longitudinal mechanical waves is the example of sound waves through a long wind pipe. So the wind pipe is like a wave guide that makes sure that the direction of propagation is one dimensional. Okay, so imagine we have an infinitely long cylindrical pipe like this. Okay. So this is basically our wind pipe, and we have taken this as our x-axis. So x is tending to infinity on this side. Okay. So over here x is equal to 0. Now, for example, to set off this type of one-dimensional waves, one of the things we can do experimentally is we can create a source of longitudinal mechanical waves by doing something like this. We can have a like a diaphragm which fits into the cylinder perfectly. Okay. And that diaphragm could be attached to a spring system like this. So basically that diaphragm is a spring mass system which does SHM along the x-axis at the point x equal to 0. Okay, so this could be the diaphragm that does SHM along the x-axis at the point x equal to 0 with an amplitude of S0. Okay, just to make it a different symbol compared to the transverse waves, here we will use the longitudinal amplitude symbol as S0 instead of E, and with a frequency F. So in this case, F will be basically this kind of thing here. So this diaphragm acts like a source for the longitudinal waves. So as this diaphragm moves back and forth like this, the air next to it also moves back and forth like this. So you can see that all air molecules in the windpipe will experience longitudinal displacements or other oscillations. So in the equation of the source at x equal to 0, some phase constant like this, where omega is 2 pi f. Should be then, assuming that the disturbance travels at a uniform speed v at any point x equal to x, the displacement becomes like this, where delta t is the delay time taken for the displacements or the disturbance to reach that position at a speed v. So if the longitudinal wave travels or propagates at speed v along the positive x-axis, then this delta t will be equal to x by v. So therefore that term omega into t minus delta t can be written as omega into t minus x by v. Or it can be written as omega t minus kx, where k is equal to omega by v or 2 pi by lambda. So we have the equation s as a function of x and t is s naught sine omega t minus kx plus phi naught. So this becomes the general equation of harmonic longitudinal wave traveling along the x-axis, okay, where s naught is the longitudinal amplitude, omega is 2 pi f, where f is the source frequency, k is equal to omega by v, which is the same thing as 2 pi by lambda, where v is propagation speed. And again, later we will see that this is a property of the medium. So it depends on medium's physical properties. It is independent of source. And of course, we have v is equal to f lambda once again. And phi naught is just a initial phase constant. So this equation now represents the one-dimensional harmonic, because the source is a simple harmonic oscillator, so it's a harmonic wave. So you can see that it is basically just like a continuation of transverse waves that we had seen. The difference is the particles are not oscillating along the y-axis. This is why we are not writing it as y is equal to a sine omega t minus kx, but they are propagating along, they are oscillating along the x-axis, and we are writing that longitudinal displacement along the x-axis with the symbol s. So s as a function of x and t in the case of a harmonic wave is a harmonic equation like this. And why it is a harmonic wave is because this acts like a harmonic source. So harmonic oscillator is acting like the source. So it produces a harmonic wave. A spring mass system, as you know, is a harmonic oscillator. Okay, so make a note of this part and just let me know in case of any doubts. So most of this section we will study as a sort of comparison with the standard, methods and definitions and concepts we had learned in transverse waves. It's just like conversion of that into a situation where the oscillation is happening longitudinal instead of transverse. But rest the concepts are all the same. Particle to particle, there is propagation of energy happening because of the oscillations transferring energy, mechanical energy from one position to another. Okay, so once we come to the equation of the harmonic wave, you can see all the various physical quantities involved in it. S naught is the longitudinal amplitude, which actually again depends on the source. It depends on how much energy or power the source is able to pump into the medium. And omega is the angular frequency of the wave, which again depends on the source's frequency. So it's the source's property. Whereas k, which is 2 pi by lambda, depends on the wave speed as well as on omega. So it depends on the wave speed, which is a physical property of the medium, which we'll discuss in a moment. So the first thing now here is the propagation speed, V. It is square root of some elastic property of the medium divided by some kind of inertia property or inertial property, you can say. Okay, Vinith, I will give you some more time to take down this information. Okay, so now in case of sound, there is longitudinal waves propagating through a fluid medium, that is liquid, or gas. Okay, speed of sound in general is given by this formula, where beta is the bulk's modulus of elasticity. Okay, and rho is the density. Okay. So in case of, for an ideal fluid that is incompressible, non-viscous, okay, density is uniform, okay, and bulk's modulus is a constant which depends only on temperature. It does not depend on pressure, for example. So for example, for water, density is 1 gram per cc, and bulk's modulus at 27 degrees C, for example, is, I'll have to look up the value, but so just note this down in the meantime. I'll just look up the value and tell you. It is about
3.12.
it's about 2.2 gigapascals. So you can see that speed of sound becomes square root of in water at about 27 degrees room temperature. It will be like this. Okay. So in general, speed of sound through a fluid medium is given by this formula. And for example, when we're talking about an ideal fluid, the density is uniform and bulk's modulus is constant, which only depends on temperature. So I've taken the example of speed of sound in water at 27 degrees. Just note down this section, then we'll see also how to calculate speed of sound in a gaseous medium, especially treating the gas like an ideal gas. So ideal gas which will obey the laws of thermodynamics, like the ideal gas equation and the standard formulae for all polytropic processes. Okay, so as I was telling you, when we are talking sound propagating through a gaseous medium, do we use the formula square root of bulk's modulus by density? It becomes a bit further the calculation. Okay, okay, Vineet, I'm waiting. No problem. Okay. Now, for a gaseous medium, treating it like an ideal gas, propagation of sound involves fast compressions and rarefactions. Of the gaseous medium. So thermodynamically, fast is equivalent to adiabatic because there's no time for heat exchange. So for adiabatic process, PV to the power gamma is constant, where gamma is Cp by Cv, or it is 5 by 3 for monoatomic gases or noble gases, and 7 by 5 for diatomic gases. So that gamma. And bulk's modulus is basically volume stress divided by volume strain. So it becomes mod of dP divided by dV by V, because volume stress in general is delta P. So for gas, bulk's modulus is removing the mod sign, you can write it like this. So in general, this is bulk's modulus for any gaseous medium. So for now in adiabatic process, the bulk's modulus, it actually becomes gamma P, as you know, because this is called the adiabatic bulk's modulus. Okay, of an ideal gas at a given state of pressure, volume, and temperature, its instantaneous value of adiabatic bulk's modulus is given by this formula, because PV to the power gamma is constant, means that this is 0, means that so this is something that you're already aware of from before. So having understood this, we now substitute. So velocity of sound and using the relation Pm is equal to rho RT from ideal gas equation, we have the formula for velocity of sound in a gaseous medium. Okay, so note down this section quickly. Yeah, so Naman, the point is like in thermodynamics, if a compression or rarefaction is happening so fast that there isn't enough time for heat exchange, then we can assume the heat exchange is 0. So it becomes approximate to an adiabatic process. So fast compression is equivalent to an adiabatic compression, because during the time of the compression, heat will not be able to flow into the gas or flow out of the gas because it takes time for heat to conduct.
Okay, sir.
So this formula actually, the square root of gamma RT by m, it has a special name. It is called the Laplace correction formula because it was understood somewhat later in the history of physics. Initially, the propagation of sound was assumed to be an isothermal process. So by derivation of isothermal bulk modulus, it was assumed that speed of sound was given by the formula square root of RT by m. But then the theoretical value did not agree with the experimental value. So people realized something is wrong. And then this correction was incorporated. So this formula is called the Laplace correction. So previously, sound was assumed to create isothermal compressions and rarefactions. So PV being constant, bulk's modulus, which is minus dP divided by dV by V, is equal to P. So but this formula gave an incorrect value. Which was in disagreement with experimentally measured values. Hence, this Laplace correction has been. So now by this formula, for example, if we want to calculate speed of sound through nitrogen gas at 27 degrees C. So we just apply this formula, but just be careful to substitute all quantities in SI unit. So gamma will be 7 by 5 for nitrogen, the diatomic gas. Temperature we'll write as 300 kelvins. R in SI unit, joules per mole Kelvin. And this we'll write as 28 into 10 raised per minus 3 kilograms in SI unit. So speed will become so this will be like close to the speed of sound in air because air is like 78% nitrogen. Yes, we need. I will take you back to the. Yeah, we need this part. Okay, so now next we move on to understanding the pressure variation, or basically the volume stress that occurs due to propagation of a longitudinal wave in a one-dimensional waveguide kind of situation, like the windpipe that we are discussing about. So basically, the molecules of air here are vibrating in this sort of direction. And this sound wave is propagating like this, such that at any point the longitudinal displacement along the x-axis as a function of time is given by this equation, suppose. So what happens as a result of that is that if you imagine a section of the pipe which is having a natural thickness of this much delta x, okay, so consider a section of air which has an unstressed volume equal to A into delta x, where A is the cross-sectional area. So this section, it is bounded by x equal to x and x equal to x plus delta x. So these are the mean positions. So during propagation of the wave, this will alternately get either expanded like this, or this is expanded, or it can get compressed also. So something like this might be happening. Or something like this might be happening, that this has a larger displacement compared to this one's displacement. What would be the case? So it can get compressed. So when the wave creates displacements of s equal to s naught sine omega t minus kx plus phi at x equal to x, and s equal to s plus delta s, that is at x equal to x plus delta x, we can see that the volume which is now stressed has become equal to delta x plus delta s into E. Okay. So just go through this section and understand this once, and then we will apply Hooke's law to that section and understand the volume stress. So how this term has come, let's understand. It's like if you have y is a function of x. Okay. Suppose this is the graph of that function. So at a particular value of x, y has a particular value. But now at a value of x, which is x plus delta x, y also has a different value, which is y plus delta y. So if y is equal to fx, then y plus delta y is equal to f of x plus delta x. So like that here, s is a function of x and t. So s plus delta s is this. So this one is the displacement at x plus delta x. At time t. Okay, so it's becoming like this. Now for small delta x, delta y can be treated as the derivative into delta x, slope of tangent concept. So when there was no sound wave propagating through it, it had an unstressed or natural volume of this much. But because of the propagation, now it has a stressed volume of this much. This is stressed volume. And delta S can be positive or negative. So accordingly, there can be a compression or an expansion. So the volume stress is equal to the change in volume divided by the unstressed on a natural volume. So it is mod of delta S into A divided by delta X. So it is delta S by delta X is mod. So the volume, so there's a volume strain or the stress. The volume stress by Hooke's law is equal to into Pulse modulus. So for instantaneous stress at the point x equal to x, at t equal to t, we should take delta x tending to 0. So some partial derivative over here, because s is also a function of time. Actually, it's not like that. I'll explain to you what it is. Just a moment. So this is actually like this. It is bulk's modulus multiplied by minus of delta S by delta X, because bulk's modulus is defined as magnitude of volume stress upon volume strain, and that is actually minus of volume stress upon volume strain, because when delta P is positive, delta V by V is negative. When delta P is negative, delta V by V is positive. That's why this mod is removed with a minus sign. So when you remove that, the volume stress is this actually. So the volume stress is now given by this form, this symbol. Okay, so this volume stress actually stands for the excess pressure at the point x equal to x at the time t equal to t. It's not the absolute pressure, it is the excess pressure. So that is equal to minus of bulk's modulus into volume strain. So it is minus of bulk's modulus into this. Okay. So cumulatively we write it as some amplitude into write it as plus pi by 2. So a longitudinal displacement wave this results in creates volume stress or pressure variation like this, where P naught is called the pressure amplitude, which means that the at maximum compression the volume stress is plus P naught, and at maximum rarefaction the volume stress is minus P naught, and at zero stress, what we call the pressure mean, the volume stress equals to 0. So this is basically now a pressure wave, you can say. So this creates alternate compressions and rarefactions. Okay. At any point x equal to x in a medium with frequency equal to omega by 2 pi. Okay, so I'll just take you through the steps of this once more. Yeah, so scrolling down, Okay, so now just putting together a few things here. So we understand that the displacement wave, so called, and the pressure wave, so called, they are both representations of a longitudinal mechanical wave. One gives the longitudinal displacement of medium particles, and the other gives the volume stress or the pressure variation. As a function of x and d. This gives it as a function of x and d. But they both represent the same thing, which is the longitudinal mechanical wave. And they are representative of this such that the pressure amplitude is directly proportional to the displacement amplitude. This is the relationship. And likewise, they have a phase difference of pi by 2. So there are alternate compressions and rarefactions which happen at a frequency of omega by 2 pi. So a compression is when this is plus p naught, and a rarefaction is when minus p. Okay, now next thing we'll study about is next property is intensity of a sound wave. So the intensity, just a moment. So intensity I, it is measured as the power propagating per unit cross-sectional area, or you can understand it as the energy per unit time, per unit area of cross-section propagated by the wave. So intensity is measured in watts per meter square. And the formula for intensity becomes like this. If you consider a section of the pipe having a thickness of dx, so the mass of particles there is density into volume. So these particles have a maximum kinetic energy of half dm into like this. Okay. So this is the maximum kinetic energy. So the mechanical energy of oscillation of those particles is that much. Again, a concept borrowed from SHF. So intensity, which is power per unit area, and so again the formula is somewhat symmetrical. What we have seen for transverse waves earlier. We just replace density with linear mass density and it becomes power instead of intensity. And replace the longitudinal amplitude S0 with the transverse amplitude A. So that becomes. Now also P0 is proportional to S0. So intensity is also proportional to pressure amplitude square, such that if you work it out, it come out to be like this, I think. Basically, in this formula, omega by k is equal to p. So that is the relationship of the intensity with the two types of amplitudes, pressure amplitude and displacement amplitude. Okay, now couple of factual things that you should know about is audible sound, that is sound audible to human ears. It has a frequency range of 20 to 20,000 hertz. Frequency greater than 20,000 hertz is called ultrasonic, and it is inaudible to humans. Frequency less than 20 hertz, it is called subsonic. It's again inaudible. So it's called infrasonic. Frequency of about order of magnitude 50 hertz, it is called subsonics. Frequency of the order of about 2000 to 5000 hertz. This is the human vocal range. Frequency in the region of 500 to 1000 hertz is typically called the bass frequencies. Frequency higher than 5000 hertz, they called high frequencies. They're called the mid frequency range. This is all kind of general information, not particularly important from exam point of view. But yeah, it's important that you know this thing, the frequency range. This much. Okay. Now like that, so frequency as a quality is more about the pitch of a sound, whereas the intensity is more to do with loudness of the sound. Okay. So there is something called threshold of hearing, which is about 1 picowatt per meter square. So this threshold here of hearing is the softest intensity audible to the, when I say human ear, we mean average human ear, because obviously each person's hearing system is unique. So it will have unique set of parameters. And most of our hearing systems are highly damaged because of all the noise pollution that we are continuously subjected to in our lifetimes in urban life. So these parameters typically do not apply to us, especially not in our adult lives. So only in the early infant life that is applicable, because that time our hearing system is relatively undamaged. So again, this is an important value to remember. Threshold of hearing. There's also something else that you can note down, though not very important from exam point of view. So threshold of pain. If intensity is greater than this value, then continuous exposure without hearing protection can cause physical pain in the ear. In the inner ear, and eventually damage. So this value is about 1 watt per meter square. So it's 10 raised power 12 times this value in watts per meter square. So that is the loudness or intensity range, you can say, from the softest sound we can hear, which is threshold of hearing, to the loudest sound that we can tolerate without pain or without damage to our hearing system. These are just a few factual things. Just note them down. Okay, scrolling up for a minute. So going back to the derivation of the intensity formula once more. Okay, so finished with this. Let's move on. So now there's another concept related to measurement of loudness, which is called the decibel scale of loudness for sound waves. So let's understand about that. Loudness or intensity actually. In the decibel scale, also called the dB scale in short form. So the decibel scale of intensity is given by a formula that intensity in decibels is 10 multiplied by logarithm to the base 10 of the intensity in watts per meter square divided by the threshold of hearing in watts per meter square. So for example, an intensity of 2 into 10 raised power minus 6 watts per meter square in decibel scale becomes 63 decibels. So that's equivalent to, in the decibel scales, an intensity of 63 decibel. Okay, so this is about the decibel scale of loudness. Now, one final thing we'll just note down about the decibel scale is important here. That if an intensity is equal to double of another intensity in watts per meter square, then I2 in decibels becomes I1 in decibels plus 3 decibels. This is called the plus 3 dB rule, or I1 is equal to I2 minus 3 decibels. So you can understand the logic of this from the above calculation. So for example, if I take I1 as 10 raised power minus 6 watts per meter square, I take I2 as 10 raised power 2 into 10 raised power minus 6 watts per meter square, and I take another one, let's say I3, which is 4 into 10 raised power minus 6 watts per meter square. So I2 is double of I1 and I3 is double of I2 in watts per meter square. So therefore, now we can see I1 in decibels will be 10 log I1 by I0. So that is 10 log so you'll see that I1 in decibels will come out to be 60 decibels. Now likewise, when you do the calculation for I2 and I3, so it will become 10 log 2 plus log 10 raised power 6. So this log 2 is 0.3. So you'll see this becomes 63 decibels. Likewise, so this thing is the same as so that's why 66 decibels. So you can see that I2 is 2 times I1 in watts per meter square. Therefore, I2 in decibels is I1 in decibels plus 3 decibels. Same way, I3 in decibels is equal to I2 in decibels plus 3 decibels, or I1 in decibels plus 6 decibels, because I3 into 4 times I1. So this is an important type of calculation you should know how to do. So note this down, and with this we finish the part which is different for sound compared to what we have seen earlier. Next lecture we'll be looking at, next lecture of sound, that is, we'll be looking at interference of sound and standing waves created. So that's superposition of sound waves, which would be the same type of treatment that we have seen for superposition of longitudinal waves. So that's it for today's session, people. Wish you all the best and have a nice day.
Thank you, sir.